Okay, so this is part 2 of 2012 question 6, higher level physics. Got a bit confused there a minute ago, trying to figure stuff out. So I'm being asked, what's the change in force from the small parachute to the big parachute? Okay, and we're saying that they're a hemisphere. Okay, it's not a very good hemisphere, but you get the idea of radius r. So the total area of a sphere is 4 pi r squared. So the area on the inside or the outside of a hemisphere is 2 pi r squared. Okay, it's half of it. Now, that's not the total surface area. It's just the surface area of the inside. But that's all I'm interested in, because I'm interested in the force that's acting on it. Okay, so the force that's acting on it changes because the area changes. All right. Because does that make hopefully that makes sense? Is that F1 is like the total pressure of the air against it, essentially against that area. Okay, so we know that pressure is force over area, which means that force is pressure times area. Okay, so if the area goes down and the pressure stays the same, you're assuming it stays the same. Obviously the air pressure will be different at different altitudes, but we're going to ignore that. The pressure F1 depends on A1, and then force 2 will depend on area 2. Okay, so force 1 is proportional to 2 pi times 4.25 squared, and force 2 is proportional to 2 pi 0.9 squared. Oh, actually, I don't even need the 2 pi. Yeah, 4.25 squared times 2 times pi. What I want to do is I want to see how much the force has increased. So I'm going to do F1 divided by F2. It'll just make the maths easier. So that is going to be directly proportional to 2 pi times 4.25 squared divided by 2 pi times 0.9 to be squared. The 2 pi is common to both of them. So I'm just doing 4.25 squared divided by 0.9 squared. And that gives me an answer of, so F1 divided by F2 is essentially, it is 22.29 times. So it's 22 times bigger, okay? How much was the force on hemispheric out parallel? Yeah, 22.29 times. There's no units there, okay? It's just 22.29 times. Just going through that again, right? Look, pressure is force over area. So force is related to area if pressure is constant, and you're assuming the pressure is constant, even though in reality, in the situation, it wouldn't be. So that means force 1 is proportional to the area of the parachute, okay? Force 2 is proportional to the area of its parachute, the smaller parachute. I'm being asked how much times bigger is F1 compared to F2. So I'm going to divide them. When I divide them, 2 pi goes into 2 pi once, it's gone, right? We're multiplying by 1, it's not important anymore. So essentially, it's just, it goes up with the square of the radius, right? So 4.25 is half of 8.5, wasn't it? Just double checking that. Yeah, 8.5. And 0.9 is half of 1.8. So we're dividing the squares of both the radii, and that's what you get. The force, the area of parachute 1 is going to be 22 and a bit times bigger than the area of parachute 2. Therefore, the force is going to be 22 and a bit times bigger as well. When I have space to go on to, I will. I'm going to do it here. I'm going to save paper and save the universe and all the world anyway. Okay. Calculate the upthrust that acted on Kittinger when he reached constant velocity in the last stage of his descent. Assume g is equal to 9.81 meters per second squared. Okay. Constant velocity means that force 1 is going to equal force 2. That there is no acceleration. Acceleration is 0. Okay? So what that means is that upthrust is equal to gravitational force. If he's not accelerating, he's reached terminal velocity with the parachute. So the F1 is equal to F2. So therefore, the upthrust F2 is just mass times acceleration, which is mass acceleration due to gravity. So what was he was 180 kilos, remember, with his gear, and we're using 9.81 here. So 180 multiplied by 9.81. So the upthrust, which was equal to the gravitational force at that stage, was 1,765.8 newtons. I don't need to say upwards because it is upwards. Okay?